Now let us discuss the sequence networks, a very important topic. So what is meant by the sequence networks? Okay, so we saw that there are three symmetrical components for a three-phase system. One is the zero sequence component, next is positive and negative symmetrical components, right? Now what we are going to do is, each of these are balanced systems, okay? So if you take the one phase, A phase of zero sequence, you will have the voltage VA0 and the current is IA0. Now we need to draw a network that is relating these two quantities, right? So that is the sequence network. So when you relate the zero sequence voltage and current, that is called as a zero sequence network. If you are relating the voltage VA1 and IA1 of the positive sequence, you will get the positive sequence network. Similarly, if you have a network which is relating VA2 and IA2, then it is a negative sequence network, okay? And the impedances, so if you are relating these both, then you will have an impedance, right? So that will be the zero sequence impedance. Similarly, you will get a positive sequence impedance and a negative sequence impedance, right? Now, since all these zero, positive and negative symmetrical components, they are balanced, okay? So whatever circuit you are going to get for A phase, the same circuit you will also get for the B phase, VB0 and IB0. The sequence network relating these two is going to be same as that of these two quantities. Similarly, for VC0 and IC0, okay, just like per phase circuits, right? In three phase balanced system, we take the per phase circuits, right? Similarly, for each sequence component, for each symmetrical component, we are going to take only one phase, that is enough for analysis, okay? So each of the power system components, it is going to have different sequence networks. So we will be discussing the sequence networks for each of them. Now a few points that you need to remember here with regard to the sequence networks. Like I said, different power system equipments or components will have different sequence networks and sequence impedances. Okay, and the second point is, in a balanced system, what is going to happen? All of these sequence networks will be decoupled. That means they are not related to each other. In an imbalanced system or unbalanced system, what is going to happen? The sequence networks are going to be interconnected, will become interconnected, okay? So that is how the unsymmetrical faults, they are analyzed, okay? And the third point is, in a balanced system, only the positive sequence components will flow. In a balanced system, only positive sequence currents will flow, okay? The negative and zero sequence currents will be zero, okay, because it is balanced. So first we will see the sequence networks of three phase symmetrical loads. So both the star connected and the delta connected loads we will be seeing. First we will deal with the star connected load. So we will have impedance here in each of the phases, and all of these impedances, they will be equal. That is why it is called a symmetrical load. We will also take a neutral, ground to neutral impedance, okay? So these phase impedances we will take as ZY, star connected or Y connected, right? So that's why we are taking ZY. And this impedance we will take as Zn, the neutral impedance. Okay. So now you can also take the currents. This is phase A, this is phase B, and this is phase C. So here this current is IA, IB and IC. And here through the neutral there is going to be current IN. And this point here also you mark, this is the neutral point. So now if you apply KCL at the neutral point, what you are going to get? KCL at neutral N. This is going to give you IN is equal to IA plus IB plus IC. In a balanced system, what will happen? IN is 0, right? All of the currents, they are going to be, if you are adding, they are going to give 0, right? So in that case, the neutral current will be 0. But in unbalanced system, IN will not be equal to 0. Okay. Now, this IA, IB and IC we are going to express in terms of their symmetrical components, respective symmetrical components. So what will be IA? This is going to be IA0 plus IA1 plus IA2, right? And IB you can write as IB0 plus IB1 plus IB2. Similarly, IC is going to be IC0 plus IC1 plus IC2. Okay. Now, IA0, IB0 and IC0, these are all equal in magnitude as well as they are in phase. Okay. Whereas IA1, IB1, IC1, what will these be? These are magnitude wise they are equal, but they are 120 degrees out of phase. They form a balanced system. So if you add these three, you are going to get 0. Similarly, if you add these three, you are going to get 0. But these three will give you 3 times IA0. Anything you can take. 3 IA0 or 3 IB0 or 3 IC0, right? Anything. So here the neutral current is equal to 3 times the zero sequence current. This is one important relationship. Okay. And also the zero sequence current, this will be equal to 1 by 3 times the neutral current. So since we are finding the sequence networks here, this equation is what we need. This we will take as equation 1. Okay. Next what we will do is, we will take the phase to ground voltages. So we will represent this as VA, VB and VC. Okay. This is the phase to ground voltage. Okay. So this you can write as what? Here if you see in the diagram, this is the phase. So from this to ground we need the voltage. So this will be equal to voltage across each phase, that is from A to neutral point and again from neutral point to ground, right? So this we will write as VAN, VBN and VCN plus again the neutral to ground voltage. Okay. So this is phase to neutral voltage and this is neutral to ground voltage. Now once again if you see the diagram, the phase to neutral voltage, what we can write, this is equal to this current into the impedance. So VAN if you take IA into ZY, VBN if you take, it is equal to IB into ZY. Similarly VCN is IC into ZY, right? So this is going to give you IA ZY, IB ZY and IC ZY. And VNG also you can write in terms of the neutral current. So what will this be? The impedance, neutral impedance into the neutral current. Okay. All of these will be Zn, In. Now these are original phasors. Okay. VP, matrix VP. So you can write as A into Vs, right? So A into A matrix into symmetrical components VA0, VA1, VA2. Similarly, this also you can write in terms of its symmetrical components, right? So this you are going to get A into VA0, VA1, VA2. This is equal to ZY also you can take out common, the matrix A, and here you will have IA0, IA1, IA2 plus ZNIN you can take out common. So 1, 1 and 1. Okay. So now here if you are pre-multiplying by A inverse, the final expression you will get here is VA0, VA1, VA2. This will be equal to ZY, IA0, IA1, IA2 plus 3ZN, IA0, 1, 0, 0. Okay. So from here you will be able to get the relation between each of the sequence voltage and currents. Okay. So what are these relations? VA0 will be equal to ZY IA0 plus 3ZN IA0. Okay. So this means that what will be the zero sequence impedance? This is represented as Z0. This is what? VA0 by IA0, right? So this is equal to ZY plus 3ZN. So if you draw the circuit here, what you are going to get? One impedance here of value ZY, another impedance of value 3 times Zn, and here you have the zero sequence voltage VA0 and zero sequence current IA0. Okay. So this is the zero sequence network of the star connected symmetrical load. Similarly, you can get for the positive sequence. Okay. So this is VA1 is equal to, from this equation, right, VA1 is equal to ZY IA1 plus 0. Okay. So VA1 is equal to ZY IA1. So here you will have impedance ZY, current IA1, and the voltage is VA1. Okay. And here the positive sequence impedance, that is represented as Z1. This is equal to VA1 by IA1, which is ZY. Okay. So this is the positive sequence network. In a similar manner, you are going to get the negative sequence network. There is no change, it is going to be same. Okay. Here only you have the negative sequence current and the negative sequence voltage. So Z2 is equal to VA2 by IA2, which is ZY. So you can see that Z1 is equal to Z2 is equal to the per phase impedance. Okay. Whereas zero sequence impedance, that is slightly different. Now the zero sequence network, it will vary for different grounding conditions. Okay. So anyways, we saw if it is grounded with an impedance, what is the network we saw? If it is grounded without any impedance, without impedance means Zn is 0. Okay. So in this case, what will be the network here? So simply going to be Zy, and here Z0 will be equal to Z1 and Z2. That means all of the sequence impedances will be equal in this case. Okay. So here IA0 and VA0. If it is not grounded, if ungrounded, okay, then the zero sequence network, this is going to be open circuit. There is no path from the neutral to the ground. Okay. So here Z0 is equal to ZY, and what will be the zero sequence current, this is going to be 0. Okay, so VA0. Next we are going to consider the delta connected load. Okay, so here you have the 3 lines. Okay, now each of these impedances we will take as Z delta. Okay, to represent the delta connected load. Now this is phase A, phase B and phase C. So the current flowing through this is the phase current IA, this is IB and this is IC. Now in order to get the sequence networks for a delta connected load, we need to transform it to a star. Okay, so why is that? Because there is no neutral to be able to get the sequence networks. Okay, no neutral, therefore we need to transform to star to get the symmetrical components. Okay, so once you convert it into star, what is going to happen? All of the impedances, they are going to get divided by 3. Right, so Z delta by 3, Z delta by 3 and Z delta by 3. Okay, but once we got it in star, the sequence networks will be same as what we derived before, right? But the zero sequence network, it will be slightly different. So I will tell you why that is the case. First we will see the positive and negative sequence network. Essentially they are the same, right? Except that here the impedance will become by 3 because we are first transforming into the star. Okay, so Z delta by 3 and here you will have IA1, IA2. What is the impedance here? Z1 is equal to Z delta by 3 and similarly the negative sequence network, this is going to be also same, except that here you have IA2 and VA2, Z delta by 3. Okay, so Z2 is equal to Z delta by 3. Okay, now we will see the zero sequence network. Since there is actually no neutral present, right, so it is like an ungrounded star, then what will be the sequence network for such a case? There should be an open circuit between the neutral and ground. But what we are going to do, there will be open circuit, there is no change in that. But this point we are going to connect with the neutral. Okay, so this is the zero sequence current IA0 and this is the zero sequence voltage VA0. What about this impedance? This is Z delta by 3. So now the question is why we have represented this. So sometimes what happens is in the delta there can be circulating currents. So in order to represent that there is going to be some circulating current, we are showing a closed loop. Okay, whereas in a star connected load that is not the case. There will simply be an open circuit. Here in addition to the open circuit we are just showing one extra loop. Okay, and here there is no significance for the zero sequence impedance. There is no impedance here. Okay, next we will see the sequence network of a transmission line, a symmetrical transmission line. Okay, so now each of there will be 3 lines, right? For 3-phase system there will be 3 transmission lines. So each of them, let us say they are having an impedance ZS. Okay, so using the subscript S to mean that it is a self impedance. So transmission lines will also have the mutual impedance Zm. Between each of the phases we are taking Zm. So now this is phase A, let us say, phase B and C. Then what will be the currents? IA, IB and IC. Now if you take some reference potential like this, okay, then this potential is going to be VAN. Similarly, VBN and VCN are also going to be present. On the other side, we will take VAN dash. Okay. So now we will write the equations. What will be the voltage drop across the transmission line? This VAN minus VAN dash. This is equal to, for phase A, right? We are considering phase A first. ZS into IA plus, due to the mutual impedance, there will be a voltage drop. Okay, so mutual impedance due to current IB as well as due to current IC. Okay, so this is one equation. This is for phase A. Similarly, you can write for the other two phases, right? VBN minus VBN dash is equal to, here ZMIA plus self impedance IB plus mutual impedance with current IC. Okay. Similarly, VCN minus VCN dash, here self impedance will be with respect to current IC, others will have mutual impedance. ZMIB plus ZSIC. Okay. So here what is ZS? This is the self impedance, and ZM is the mutual impedance between the transmission lines. Okay. Now these three equations that we have here, these are in terms of the original phasors. Now we will express in terms of the symmetrical components. Okay. So then what you are going to get, A into VA0, VA1, VA2 minus A into VA0 dash, VA1 dash, VA2 dash. This is equal to ZS, ZM, 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 ZS, and again ZM here, and finally this is the last row. Okay. So instead of IA, IB and IC, we will write in terms of symmetrical components. So this is A into IA0, IA1, IA2. So now we pre-multiply with A inverse. Okay. So here you are going to get A is now going to vanish. VA0 dash, VA1 dash, VA2 dash. This is equal to A inverse ZS, ZM, ZM, this matrix, right, same matrix, ZS and then A, and here you will have IA0, IA1, IA2. Okay. Now this three matrices here, A inverse into this matrix into A, this if you calculate, you will get, you can try it later, I will write the final expression, ZS plus 2 ZM 0 0 0 ZS minus ZM 0 0 0 and finally ZS minus ZM. Okay. So now you can write the sequence networks. Okay. Zero sequence network if you take, what is the equation here? From here you can write VA0 minus VA0 dash is equal to ZS plus 2 ZM into IA0, right? We are getting decoupled equations here. So VA0 minus VA0 dash is equal to ZS plus 2 ZM into IA0. Okay, so you can draw the circuit as well. Here you will have an impedance Z0. Okay, so is equal to ZS plus 2 ZM. This is the reference. Okay. Now what is the potential at the receiving end, starting end? This is VA0. Okay, and this is the current IA0. And what about this voltage at the receiving end? VA0 dash. Okay, so this is the zero sequence network. And next we have the positive sequence network positive sequence and negative sequence network are going to be same. Okay. So here you have the impedance Z1 is equal to Zs minus Zm. And what are the voltages here? VA1 and VA1 dash. And this current is IA1. And similarly, negative sequence network you can draw. Okay. So you can see that the zero sequence impedance, this is going to be larger than the other two, right? Z1 is equal to Z2 is equal to Zs minus Zm. Next we will see the sequence network of a synchronous machine. So here there is no derivation, we will directly see the sequence networks. The positive sequence network, we are going to have the internal voltage, okay, and one impedance. So this is usually equal to the synchronous reactance if the machine is in steady state. Otherwise it is equal to the subtransient or the transient values. Okay. So this terminal voltage is going to be VA1. Okay. So here IA1 current flows. This is for each phase, right? So you can see for each of the three phases also. So this is just for the sake of clarity, right? All the three phases we are showing here. So this is phase A, this will be phase B, and this is phase C. What will be the current that will flow here? IA1, this is IB1 and IC1. So these are A, B and C, and this point will be the neutral. Okay, so these are the impedances Z1. What will be this internal voltage? EAN. Similarly, this is going to be ECN, and this is EBN. Okay, so this is for all the three phases we are just representing. Next, the negative sequence network. See here, the negative sequence impedance, it is not going to be equal to the positive sequence impedance. Okay, so that point is important. It is just going to consist of an impedance. In positive sequence, we had the internal voltage. Here there is only impedance. Okay. Now the current IA2 will come out like this, and this will be the voltage VA2. Here also you can draw the three phases all together. Here it is only going to consist of impedances. Okay. So this is phase A, B and C. What are the currents here? IA2, IB2 and IC2. This is the neutral point. This is the impedances. Okay. So here Z2 is slightly less than the positive sequence impedance Z1. Next, the zero sequence network. Here you are going to have two impedances. This point will be the neutral point. Okay. So what is this impedance here? This is ZG0. This is the zero sequence impedance of the machine, the per phase impedance of the machine. And here you will have 3 times the neutral impedance. That means from neutral to ground, if there is an impedance, that into 3 times. Okay. So this entire thing will now be the total zero sequence impedance. Okay. So what will be the current here? IA0, and this voltage is VA0. So you can draw for the 3 phases also you can draw. This is phase A, B and C. Now if this is the neutral, then you are going to have the neutral impedance here, Zn. And what about this? This is Zg0. Okay, so you write down here, otherwise you will get confused. Here Zg0 is the zero sequence impedance of the machine. That means it is dependent on machine. See, same goes for positive and negative sequence components as well. Z1 and Z2, they are dependent on the machine parameters. Okay. So, this is the per phase impedance. Now, here how the currents are going to flow? Here you are going to have I E naught. This is I B naught. This is I C naught. Okay. And this will be the neutral current. This is going to be 3 times I A naught. I B naught, I C naught also we can take. All of them are equal, right?